Okay, let's get started. So, any question from this time? I think today we'll just finish the properties of this transform, and yeah. So today will be the last class of this course, and next week we'll have our final. Okay. So let's start with a bit of a review on these properties of Z transform. So properties of the Z transforms are very similar to properties of Laplace transform. So also which is also similar to the properties of Fourier transform. And so for example, we have the property like linearity such that you have a small x1 plus bx small x2, then it really transforms to a big x1 plus b big x2. But just like Laplace transform, we need to think about what happened to the RC. Okay, so in linearity, we have that the RC of the resulting linear combination will be RC containing the intersection of RC for a big x1 and RC of big x2, and we have containing here because we might have some pole zero cancellation, just like in Laplace transform. Okay, so many properties are very similar to Laplace transform, except that the RC are now circles or rings, and while in Laplace transform the RC are strips. So there is some geometrical difference between the Z transform and the Laplace transform. Okay, let me try to do this. Okay, and yeah, so this is linearity. Then we have time shifting. And okay, so here we see like a different form. So in time shifting, we say that if we shift the time domain by n0, so x becomes x of n minus n0. Then in this frequency domain or z domain, we get extra z to the minus 0 factor. Z to the minus 0 factor. And ROC is the same, except that you might add or delete some poles or some poles by this z to the minus n0. Okay. And then we have the scaling in time domain, scaling in z domain, which is this funny thing. So basically we shift our z domain by some z0. Okay. And so we change every z to z times z0 basically. So like we think about if we shift everything in the z domain by z0, so basically doing this change. Okay. So we change everything to z0 times z. And so for example, you have a pole 0 at z equal to a, then the pole in 0 shift to z0 times a. And if we do that, then that's like you shift your then your big X of z will become big X of z divided by z0. And ROC will be, the ROC was a circle, and it will circle a ring. And so ROC, because it has this polar symmetry, so ROC will become absolute value of z times this ROC. So absolute value of z0 times the same ROC. So yeah, so this say if it was a circle, then the circle will get shrink or expand by the factor of this absolute value of z0. And so if you change so that's on the z side. If on the frequency domain you shift by some z0, and then on the time domain will shift by z0 to the nth power. And so you can think about this like in the I guess you can think about this as in the Laplace transform. You shift your s by s0, then you get extra e to the s0t factor. And e to the s0 is like a z0 here. Okay? And yeah, so this is this. And we have an example saying that showing how this shift by z0 works. Okay, so if your z0 is pure phase complex number, so here z0 can be any complex number. So if your z0 has a unique length, so it's just e to the some j, e to the j omega 0 for some real value omega 0. And then it's like you are rotating everything on this z plane by angle omega 0. Okay, so if your h of z, big X of z has 0 here, 2 0 here, and a pole here, then everything gets rotated by omega 0. So this 0 here gets rotated by omega 0 to here, this pole here gets rotated by omega 0 to here, and this 0 gets rotated by omega 0 here. And the ROC is still the same ROC because you say the ROC is some circle or ring outside, and you rotate the whole ring, the ROC doesn't change. So ROC is the same, but the location of everything got rotated by some omega 0, and that's equivalent to you doing some frequency change. Okay. So for example, you think about the Fourier transform. So Fourier transform is you restrict your x of z to this unit circle, okay? And so now you think about that, then that's corresponding to you doing a frequency shift in your Fourier transform, because getting this HRZ0 equal to e to the j omega 0, and you plug in this formula, your x of z becomes x of z divided by z0, and dividing z0 means times e to the minus j omega 0. And then you also use for the Fourier transform z equal to j omega. So combine these two, you see that omega changes to omega minus omega 0. And so this kind of z shift is same as you doing a frequency shift of omega going to omega 0. And on the other hand, you will have your time domain x of n multiplying z0 to the n. And z0 to the n is e to the j omega 0 n. And you see that this is exactly the frequency shift formula of the discrete time Fourier transform. Okay, so you shift omega to omega minus omega 0, you get HY e to the j omega 0 n vector. This is the formula we had in chapter 4. Oh, sorry, chapter 5. Okay, and then we have time reversal. It's kind of similar to before, but a little different. So before we have that whenever you have a minus sign on your time domain, you also get a minus sign on frequency domain. And but now this z is like e to the s. So when you take exponential, this minus sign give you one become inversion. So this minus s translates to 1 over z. Okay. So you get a minus sign on your time domain, you get inversion on your z domain, you get 1 over z. And also you have associated ROC change, so ROC become 1 over r. Okay. And yeah, so here is some explanation of this 1 over r. So if you had z0, if you had some z0 point, and then it will become 1 over z0. Okay. So say this is a pole 0, then you have pole 0 at 1 over z0. Okay. So that's from this time. And any question? Otherwise, let's keep going. Okay, and then we have time expansion. Okay, and so time expansion, we introduced this in chapter 5. And just as a small reminder, we want to do this because we're saying that it's hard to do expansion or compression for discrete time signal. Because if we do compression, then we will lose information, because at some point we will map to this fractional point, and we just cannot. And but if we do expansion by non-integer multiple, we are also going to map things to some non-integer point. So the only thing you can do is we do this expansion by integer multiple. So say here is the example of a discrete signal, and we do this time expansion with a factor of 2. And so what we do is we insert 0 between each of those signal spikes, and just move these far away from each other. So for example, this spike got moved to this spike at t n equal to 1 got moved to this spike at n equal to 2, and n0 still moved to n0, and this n02 spike got moved to n equal to 4 spike. And so you see this 1, 2, 3, 4 got mapped to 2, 4, 8, 6. So sorry, 2, 4, 6, 8. And we just have a 0 in between those spike points. So this is exactly this complicated formula saying. So we have this x sub k means that we do time expand of a factor of k. And so every point is moving away to like by a factor of k away. And you just put 0 in the HR slots here. So you lose no information, and everything is stretched out. Okay, and so now back to time expansion. So this is a time expanded signal we have, and now we want to see what's z transform is. So if our original signal has z transform big X of z, then time expand signal will have z transform to x over z to the k, and with ROC being r to the 1 over k. And so what does this mean is quite funny. It means that you, oh okay, finally. And so this is funny. This means that you kind of compress your ROC to 1 over k factor. So you compress your ROC by 1 over k factor, and that means two things. You either shrink or expand your radius a little bit, and also the angle also got multiplied by 1 over k. We'll see an example very soon. Okay. And this also means that you have pole 0 at A, and you have pole 0 at A to the 1 over k. Okay. And but it's actually more complicated than this. So let's actually see a more complicated, more concrete example. So we have our favorite example of Laplace transform kind of like this. Okay. And so if we have Laplace transform, this is Laplace transform of exponential decay function, and it's like 1 over 1 minus a z to the minus 1. Okay, so we have this 1 over 1 minus 8 and to the z minus 1, and with the ROC being z greater than 8. And so this thing, obviously, when z equal to 8, it's 1 over this. When z equal to 8, it has a pole because it's 1 minus 8 divided by 8. Okay, so at z equal to 8, so it should be very far away. At z equal to 8, it has a pole, and I think it has a 0 at 0, z equal to 0, but we don't care right now. Okay, so it has a pole at z equal to 8, and we say the ROC is outside because we pick so. Okay, so this thing, and so what happened when we compress the time domain by a factor of 3? Expand the time domain by a factor of 3, and you will become something. And but what I want to see is what is the signal that x to the, now we have the x to the z to the k. So z to the k, so every z becomes z to the 3 because we say k equals 3. And so now we have this signal 1 over 1 minus 8 times z minus 3. And so this thing actually has 3 poles. Okay. And so we want 1 minus a to the z minus 3 equal to 0. And so that means the z cube equal to 8. Okay. And so z cube equal to 8, and obviously there is a pole at z equal to 2. Okay. At z equal to 2, there is a pole, but we are in complex domain, so there are actually 2 other poles. So at this 2 times e to this angle, and 2 times, I guess that's right down. So you have a pole at 2 times e to the j 2 pi divided by 3, and you have another pole at this 2 times e j 4 pi divided by 3. Okay, so you actually have 3 poles, and ROC is like, yeah, ROC is outside of this. ROC is outside of z equal to 2. Okay, and okay, so this complicated thing. So you see that when you change the z to the k, so actually you do quite a bit of things. So first, the ROC being a circle, its radius might change. So if its radius was greater than 1, then you see that it takes this 1 to the k power, then the radius will shrink, right? And yeah, so it was 8, and now it's 3, 8 to the 1/3, and it's 2. And obviously, then if you have something smaller than 1, say it's 1 over 8, then it will become 1 over 2. So it will shrink, or it will either shrink or expand toward this z equal to 0. And also there is this funny thing that you kind of compress and copy it, right? Because you see that okay, you had a pole at this 8, and okay, you had a pole at this z equal to 8, and now you have this pole at z equal to 2, as we say here. but you also get a pole at this z equal to 2 times e to the j 2 pi divided by 3 and 2 times e to the j 4 pi divided by 3. Okay, so what happens is like your x of z kind of got compressed by factor of k. So this whole circle is now this whole circle is compressed to 1/3 of a circle and got copied twice here. Okay. So this is what happened. So you get everything got compressed by 1/3 in this example, and then you got pole here, but it's also good because you can compress by 1/3, but you need to be the full circle. So actually you got the copy twice. So you had this pole here got copied 3 times. So you had 1 pole here, and then now you have 3 pole, and you can generalize these to higher order. Okay. And any question? So yeah. And this kind of fit our expectation in general of this expansion or compression in time frequency domain. That is, we do expansion in time domain, then we get compression in frequency domain. So this frequency domain, frequency is kind of the angle here. So like we expand the time domain by a factor of 3, then frequency domain got compressed by compressed by a factor of 3. So it was 1 circle here, and then now it's 1/3 circle, and just repeating itself over 3 times here. Okay. And yeah, so that's time expansion. And now we have we can get a kind of interpretation or a kind of derivation of this formula. And so we do this backward. So we see that we so we have this formula, and we are trying to derive this backward, which is starting with this thing, and then we say it corresponds to the z transform of this signal. Okay, so we're starting with x over z to the k, and we know x over z is summation, so this is just the z transform formula. X over z equal to summation n, and x over n z to the minus n. And then x over z to the k is summation x over z to the k times minus n, and z to the k to the minus n is just z to the minus kn, and and then you can do change of variable because you look at this thing, and yeah, you look at this thing and you see that it only has value at it only has value when this kn is basically integer multiples of k, right? So you see that this kn must be integer multiples of n, and if you think about it, it is summation from all the n, and then yeah, so this kn will be if you think sum about everything, then you will see that you are only summing over integer model of k, and that's exactly what's doing here. Your xk of n only have value at integer multiple of k, integer multiples of k, and yeah, and so if you compare this formula and this formula, you will see that you are basically summing all the expanded all the x of n, and that's x sub k of n. Okay, and yeah, so you see that because this k must be integer multiple of k, then you are summing over all n and only at the integer multiples of k. And yeah, that's equivalent to your x of n change to this x sub k of n. Okay, this is a bit more complicated. Question. 上一张同一片。下一张，那下一张就是这张。它再上一张吗？嗯。这一张就是说，等一下，发生什么事？哦，在这里。对，这一张是说上面这个图，其实我没有画完，我应该画一下左边，对不对？就是这里还有一个，然后之类的，然后这里会还有一个，就不画。这个是说上面这张图，如果我把它 expand， 然后 k 等于2的话，它会大概长这样，就是所有东西往外推2倍。然后中间差0，就是0的地方不变嘛，0的还是0的，然后所有的这些 spike 都往外推，就是它往外长2倍，然后中间多出来的地方我们就补0， 那是等价于这个 formula 这样子。然后，就是对间隔变大，间隔变2倍，对，所以在 time domain 间隔变2倍，那我会发现，在 frequency domain 就是角度会被压缩成1/2，那如果变3倍的话，角度就压缩成1/3这样。对。Okay, so that's a bit more complicated, the time expansion formula, and and then the next one is more familiar, is the conjugation, and we skip it all once again. We skip derivation here. But what happened is that if you do complex conjugation on your time domain, and then you will also do complex conjugation on your frequency domain, so x become big X star, but you also need to do something extra. You also need to take complex conjugation on your z, so z also becomes z star. I think the derivation is you take the excuse me. Derivation is probably you take the z transform equation and just take complex conjugation on both sides. Okay, and as we always do, so we have this formula, and we want to study a special case where in a time domain you have a real signal, because a lot of time in time domain we have a physical signal, and a physical signal should be real. Okay, so if you have a real signal, then we just equate these two things on both sides. So x of n will equal to x star of n, and that means x of z, big X of z will equal to big X star of z star. Okay, and then another thing that we do often is we change this to a more familiar formula. That is, we take complex conjugation on both sides. Then x of z star will equal to x star of z. Okay, so that's complex conjugation. So that's once again. So if you have x star of n, it will z transform to big X star of z star. Also for this thing, the RC doesn't change. The RC is the same. Yeah. And okay. And also if x of n is real, then big X of z star will be equal to a star of z. Okay, and from this equation we see that if x of n is real and it has pole 0 at some point z equals to z0, and it will has pole 0 at z equal to z0 star. And so it was something similar to what I have at Laplace transform. And but if you draw in picture, means that say you have a pole here. So you say you have a pole here, and you must have a pole that's also here. So at z star. So complex conjugation means that you flip around this real axis. And similarly, if you have a 0 at here, you have a 0 at here. Complex conjugation means you take a symmetry around this this real axis. And the derivation is simple because from this formula here. Okay? And so say you have a 0 here, so so you have so this point is 0, and so you think about this point. So x of z star. Let's write this again. Okay. So for example, if we have x of z0 equal to 0, then we think about what's x of z0 star. And by this formula, this is equal to x star over z0. And that's the complex conjugation of z0, which is just 0. Okay. And similarly, if it's pole, means that it's infinity, then we think the complex conjugation of infinity is also infinity. And so we see that if at z0 is infinity, then at z0 star is also infinity. Okay, so this was the same derivation as we had in Laplace transform. Okay, and then finally we have the convolution property, which we have a very short slide here. But as always, the convolution property is very useful because it let us analyze LTI system. And anyway, the convolution property says that if you have the convolution in the time domain, you have the multiplication in frequency domain. So x1 convolution with x2, then is z transformed to big X1 times big X2. And the ROC will be containing intersection between R1 and R2. Okay. And we say containing because R1 and R2, because this multiplication here might give you some pole zero cancellation. And in the homework you might see some tricky case where you see the intersection and the pole zero cancellation has some ordering issue. Okay. And anyway, so this let us solve the LTI system because you think about say x2 is h. So this let us analyze the LTI system because if you have x1 equal to the input signal some x of n and go through some LTI system with impulse response h of n, and then the output will be x of n convoluted h of n, and then we know in the frequency domain you will just be the big x1 over z times the big h over z. Okay. This is what we've been doing since chapter 4. Okay. But now we can analyze this for more systems because because in chapter 4 and chapter 5, remember we need that the output has we need the output to actually have a Fourier transform to use this, and basically that means the output needs to be stable. And now we can have output not even stable, but we can still do the transform. Okay, and we'll see more example of this later. And let's start with an easy example of very converging h of n. Okay, and okay, so very convergent h of n. So y of n equal to, as we said, y of n equal to h of n convoluted with x of n, and our h of n is the difference of two delta functions. Okay, and so h of n is delta of n minus delta of n minus 1, and we can easily do this transform because we know the transform of delta function shifted by some signal is just shifted by some constant is just z to the power, z to the minus that number. Z to the minus that number. Okay, and so delta of n, in particular delta of n, z transform to 1, and delta of n minus 1, z transform to z to the minus 1. Okay, so yeah. And so the z transform is very easy, is z transform of delta function. And we can have the pole zero plot, and it's here. So it has a pole, obviously when z equals 0, this diverges, so you have the pole at 0, and z equal to 0, and it also has a 0 at z equal to 1. When z equal to 1, then it's 1 minus 1 is 0. Okay, so pole 0 plot, look at this. Okay, and the RC will be everything. So, excuse me. So the RC will be everything because it's a finite duration signal, and except the origin. And so origin and the infinity. Remember in section 10.2, we do a lot of discussion on this. So you need to check the origin and the infinity mode. And the origin is obviously not in ROC because we already drew a pole here. And the infinity is actually in ROC. You can just check here. So 1 minus 1 over infinity is 1, so the infinity is converged. Okay, so ROC is everything except the origin. Okay. And okay, and then now we use our convolution property, and we say that if we have x of n transform to frequency domain become big X over z, and with some ROC. And then we will have 1 of n by the convolution formula should be so the algebraic part should be the multiplication of the two algebraic parts. So this is 1 minus z to the minus 1 times our big X over z. So yeah, so this is using our convolution formula. We see the z transform of the output signal. Okay, and the ROC will be the intersection of the ROC of everything, and intersection with the ROC of R here. So it's basically the whole R, but we also have a pole here and a 0 here, and so what this pole here and the 0 here do is that you might delete the pole at z equals 0, or you might okay. So it's a bit funny. So you have pole z here and a 0 here. and so the logic is a bit long. Okay, so pole here might add another pole to the ROC of this R at at 0, and the 0 here might remove a pole at here, and so if you think so that's about adding a pole here or removing a pole here. And when you think about what adding a pole or removing a pole doing to the ROC, and what I do is in my so adding a pole might delete z equal to 0 from the ROC, and removing a pole might add this to the ROC, and also removing a pole here might extend the ROC to if the ROC was bounded by a pole here, and this might make the ROC larger. Okay, so that's what a possibility to happen to the ROC. So I guess here it's possible to have more. So when you add z equal to 1 to the ROC, and it might extend. Okay, and extend R here. Okay, so that's what possibly happen. Okay, and also for the system, also this system is a very nice system. We think a lot of time is the first difference of the system. Okay, because you think about what happened in time domain, you are taking delta of n minus delta of n minus 1 convoluted with your x of n, and delta of n is the identity system. It gives you just x of n, and actually delta of n minus 1 gives you time shift. You convolute it with x of n, it gives you x of n minus 1. So this is the difference of x of n with itself. So n step of y is the n step of x minus the previous step of x. So that's the first difference of your x of n, and it's like the so the first difference is like a discrete time variant of the differentiation. Okay, so this formula is like the discrete. So this formula here, or this property here, is like the discrete time variant of the differential property, and here's the differential property. But as we always think, the differential property is quite different between discrete time and continuous time. So for continuous time, you take differentiation in the time domain, you get the HRS here, and for the discrete time, you take differentiation difference on your time domain, and you get this weird 1 minus z to the minus 1 factor. This is just what happened. Okay, and the CMO property about this convolution formula. So we see first difference, and then now see its inversion, which is accumulation or summation. Okay, and so we assume we have output W of n being the summation of x of n from time minus infinity to your current time n. So this is accumulating your input signal from all the way to minus infinity to current time. And as we have seen in chapter 1, this is equal to, you just convolute your x of n with this unit step function u of n. Okay. And now we do z transform on both sides. Then we see the z transform of w of n will equal to multiplication of z transform of u of n, and multiplication of z transform of u of n, and z transform of x of n. And the z transform of x of n, we just think is some big x of z. And the z transform of u of n, we actually already know, because it's a special case of this z transform of alpha to the n u of n. So if you take a to the n u of n, so you take a equal to 1 here, this is just x of n equal to u of n, and a equal to 1 here, then you have 1 over 1 minus z minus 1. Okay, and so we know z transform u of n is just 1 over 1 minus z of minus 1, z to the minus 1. And yeah, so the ROC should include the intersection of the ROC of x and with the ROC of this unit step function, which is z greater than 1. So ROC is include the intersection of your ROC of x and z greater than 1. Okay. And we see that this is a counterpart of the integration property that we had in Laplace transform. So integration property, we have that you have integration, then it's 1 over s integration on the time domain, then in the frequency domain you get extra 1 over s, and yeah, then the RC is the intersection between RC will contain the intersection of your original RC and this real part of s greater than 0. Okay, so you see that at least the RC is similar, so you have at least the intersection, and the RES greater than 0 got changed to this z greater than 1, absolute value of z greater than 1. Okay, and yeah, so and also I guess a few things to check. So you see that the summation is really inversion of inversion of the first difference, because you have if you multiply this with this, you get back 1. Okay. Okay. Question? No question. Then let's go to the next property. And next property, we have differentiation in the z domain. And but now this is really weird, but this is just what happened. So the differential property on z domain, we actually we don't have the next property of just d big x dz here, and we need an extra factor of z here. So we have you have dx dz, and also multiplying z back here, then is z transform to nx of n, and the RC will be the same RC, and you can derive this by okay. You can derive this by just taking ddz on the z transform formula here. So you take a ddz here, then you become dx dz, and and on this side you only get a differentiation on z, and so you take differentiation on z, you get a minus n factor, but you get a minus n factor, so that account for this minus 1 and n, but z also become z to the n also become z to the minus n also becomes z to the minus n minus 1. So the extra minus 1 power of z becomes this z here. Okay? And yeah, so that's the derivation of this thing. And yeah, so this is very different. You get the extra z factor here. And we just remember. Okay. And let's see an example of using this. So you have our example of this thing. We did z transform on this using Taylor expansion and looking at the power series, and here we use another property to do the derivation. So big X of z equal to a log of 1 plus a z to the minus 1, and with z greater than a. Okay. And so we try to use a differentiation formula here, and we can kind of see why we want to do this here, because we have a log here, and we kind of know the differentiation of log is like 1 over x. Okay, so if you do differentiation on this side, then this become something like similar, something about 1 over 1 plus a times z minus 1, and there is other factors here. Okay, and in particular, so what happens is you do differentiation, then it becomes a rational formula here. Okay, so yeah, and so if you count all the factors, so this is minus z here, etc., and also the extra differentiation of 8 times z minus 1, a to the z minus 1, then you see this side. So this side of formula, this minus z times d big X dz is a z minus 1 over 1 plus a z minus 1. And so this becomes a rational expression of z, and we know how to do inverse transform of this rational expression of z. And on the other side, we have n times x of n. And as we said, the ROC doesn't change. Okay? And so this is a rational expression, and we can do partial fraction expansion to invert it. Okay, Uh, so yeah, so now we know how to invert this, so we can do partial fraction expansion to invert it. But now we do, but because this is in particularly nice form, so we can do this a bit smarter. A bit smarter is we try to use time shift property to do this. And the idea is that, so we see that without this a to the z minus 1 factor, then it's something we know, right? So without a to the z minus 1 factor, is this 1 over 1 plus a to the z minus 1. And that's just our favorite formula of minus a to the nth power u of n, the favorite exponential function cut off at n equal to 0. And so you get the extra a here, you get extra a here. And so our formula was minus a here, but it become plus a, so you have minus a to the nth power. Okay. So yeah, so it's minus of minus a here. Okay. And so we know this formula, and if we don't have a z minus 1 here. So so how do we add z minus 1 back is we use the time shifting property. Okay. So this will be a bit faster than you doing partial fraction expansion. Doing partial fraction expansion, you need dividing those two, get the extra constant term, and you need to do some cancellation thing. And anyway, you got this thing, and to get the extra z minus 1 factor, you can just use time shifting. Okay, because we have this time shifting formula. We say that if you add the extra z to the minus n0 factor, you just shift your n to n minus n0. Okay, so if you shift the n to n minus 1, so all your n become n minus 1, n become n minus 1, n become n minus 1, then you will get the extra z minus 1 factor here. Okay, and yeah, so that's exactly our exactly the z transform of this part. Okay, and we know this is equal to, okay, so from the previous slide, so let's copy here, and we know this is equal to n times x of n. Okay, and so what we actually want is this x of n, then we divide this whole thing by n, and so we see x of n is just this whole thing divided by n, and we clean up a little bit, so this a cancel with this minus 1, and we take extra minus sign out, so it's minus for this minus 1. So when it's a cancel with the minus 1, you actually also get the extra minus sign left over, so it becomes minus times minus a to the n, and dividing n from here, and u times n minus 1, u of n minus 1. Okay, any question about this example? And yeah, so that's the derivation of this the derivation of this retransform of a log function again, and this should be the same as our derivation for the power series from the power series. Okay, and no question. Then let's see another example. Okay, and this example is, well, this is for our partial fraction expansion. So that's the higher order of partial fraction expansion. And unfortunately, it's not quite, it's looking a bit different. Okay, so it's not quite just 1 over 1 minus a times z minus 1 to the some power. Okay, previously it was just that, but here this is a nicer form to use. So our x of z equal to, we get the extra a to the z minus 1 factor here. So our x of z equal to a times z minus 1 over 1 minus a times z minus 1 to a square. And then we use the differential property on our favorite example 10.1. So example 10.1, we have a to the n u of n, d transform to 1 over 1 minus a d to a d times minus 1 for, and with our c z greater than a, and we take a d on this side, and times minus z, then we kind of see why we have this here, because then this is exactly what we got here. So we will get this a times z minus 1 over, so this side is exactly a times z minus 1 over 1 minus a times z minus 1 squared. So you just get square power here, and yeah, so the extra weird factor just get back to a times z minus 1 on the numerator. And so on the left hand side, we know it will correspond to you get an extra n. So you get extra n here, then you get a lowercase squared, and the uppercase is a times z minus 1. Okay, and yeah, so it's a bit weird, but this is a formula that we like for use for to use for our partial fraction expansion of higher order in the Z transform. Okay. And yeah, and I guess the reason we like this is if you don't have this factor, then this you don't have U of n here. Okay. Yeah, that's just a bit weird, a bit different from the Laplace transform. Okay. And any question? No question, then I think we can do initial value theorem and take a break a little earlier. Okay, and I think the final property is the initial value theorem. Okay, initial value theorem, just like before, we require this condition. So x of n equal to 0 for n less than 0. Okay. And then the initial value now is easier than the Laplace transform. It's the initial value. So x over 0 is just equal to big X of z taking z to infinity. Okay, and yeah, and this is very easy to derive now because you still think x of z equal to the summation n from minus infinity to plus infinity x over z to the minus n. And so if your x of n equals 0 for n less than 0, means that you don't have any negative. Means that you don't have any positive over z here, positive power of z here. So this is back to the section 10.2 analysis. So for n greater than 0, you have a z to minus power. For n equal to 0, you have x over 0 here to no z. Okay. And for n less than 0, you have positive power over z here. Okay. But you don't have n greater. You don't have n less than 0 because of this condition. So you only have this z to the minus n power, and those z to the minus n power go to 0 when z goes to infinity. And so very easy derivation is that yeah, when z goes to infinity, all those negative power of n go to 0, and so you're only left with n equal to 0 term, and which is just x over 0, and yeah. So x over 0 equal to z equal to infinity x over big X of z. And yeah. Yeah, so this is basically for causal signal. And also, if you have a rational signal, you will often express your x of z as a ratio of polynomial. So you will have some n of z divided by big N of z divided by big D of z, and and so if you want x over 0 to be a finite value, then you go to infinity, this thing to be finite, and then the order of n of z need to be smaller or equal to the order of d of z. Otherwise, this will go to infinity faster than this go to infinity. Okay, and let's just see an example of initial value theorem really quickly. And this theorem has uses in various analysis of a system, but here we just use it to do something very simple. That's checking our calculation is correct. So we had that we had in a previous example. So example 10.3, we say that if our x of n equals this signal, then our x of z equal to this signal. Big X of z equal to this signal. And we just check the initial value theorem works here. So this signal, first of all, we need to check that it's causal. You need to satisfy this equation, and indeed because you have u over n both here. And for x over 0 is 7 minus 6 is equal to 1. And then big X of z when z goes to infinity, is will all those e to the minus 1 go to 0, so it's 1 over 1 times 1 is 1. Okay, so we see the initial value 0 checks out. Okay, so that's all properties of Z transform, and let's stop here and take a 10 minutes break. Okay.
这个丢进去，就是它会有，就像之前说的，会有力图的负的 power 的 part 跟 v 的零的 part 的感觉，所以应该这样说吧，它会有力图的负的 power 的 part， 就是n 大于0吧 ，n 大于0是 1 over 力图的 some power 这样的，然后 n 等于0就是 x over 0这样子，对吧？n 小于0是除了3 power 的，对吧？那总之这个 part 就没有，因为我们说它都是0，对吧？没有 n 小于0的 part。然后我们 take 力图 infinity 的时候，那这个就变成0，因为它是1 over infinity 除了3 power。
所以这里没有写出那个 n 小于0是没有东西。
有啊，不是在这里吗？这句话。
可是这一句话它不是。
对啊 ，n 小于0的时候是没有东西的 ，n 小于0的时候 x n 是0，所以就是这个 x n 都是0。对。
然后，所以。这里，然后之后这两个特图忘记。
到无限大的时候，这些全部消失，就剩下这一项。那这一项就是 x 0，它的 d 不管变多少是 x 0，因为它是x 0除了 d 的零次方。对，所以我们知道 z 到无限大的时候就只剩 x 0。如果前面这个是 x 的话。就是把它前面的套进来缺个一次。现在这个是之前我们有算过说 x 跟这个东西的话，那 b x 是这个东西，然后你就把左边跟右边都缺个一下嘛。对，这个东西套 n 等于0的话，那就这就是1，所以就是7.6，所以就是1嘛。对啊，那所以这边是1嘛，那我们缺个另外一边，另外一边这个东西 z 到无限大的话，那所有这些光会都变成0，所以1除以1乘以1就是1这样。就是其实这不是个游戏的测试。如果你的 C 测是说我 satisfy 这个 equation，然后 satisfy 这两个 equation 的话，那其实它不是个游戏的 C 测。
OK， get started. Let's finish the last part of this today's course and all courses. And so yeah, as you see here, we have the properties of Z transform, so linearity, time scaling, and the scaling in Z domain, etc. And as you see that we start with this weird time expansion property where the RC become R to the 1 over K, and they actually so you compress your RC to the 1 over K's power, but you also need to but actually have K copies because you compress the angle to 1 over K, but the angle should be always from 0 to 2 pi. Okay, and yeah, so conjugation, convolution, first difference, accumulation, differentiation, etc. And in differentiation, we see that it's a weird property because you want when we take a d big X dz, also multiply HRZ here. Okay, and yeah, so that's a property, and here we have some common Z transform pairs, and I think it's nice to look through that. And one we so we can use both. Okay, and one we like a lot is delta of n, and delta of n Z transform to 1, and RC is everything. It's actually the everything including 0 and infinity. And this is actually the only signal that I have RC being everything including 0 and infinity. And also we have some shifty version of it, delta of n minus m, and that's just z to the minus m. And so those two are very nice. It gives us the power series inversion of the Z transform, and delta of n minus m, your RC will be everything except sometimes you include 0 and sometimes include infinity. Depend on whether you have positive or negative power here. You have like a negative power here, means m greater than 0, then this will then at z equals 0 it doesn't converge. And if you have only positive power here, meaning m is less than 0, then at infinity this doesn't converge. Okay. And then we have this thing, our favorite two example, alpha to the n u of n, and minus alpha to the n u of minus n minus 1. So this is right-sided and this is left-sided. And the algebraic part is both 1 over 1 minus alpha times z to the minus 1. Okay. And they have the same algebraic expression, and one of them has RC being right-sided for time domain being excuse me, right-sided. The RC is outside-sided, so the RC is outside is polar alpha, and for this left-sided function, the RC is inside, so inside is polar alpha. And then a special case of them is when alpha equals 0, then you have this u of n and minus u of minus n minus 1. Okay. And then for the higher order, we use a differential formula to derive this. Okay, so those are things that you can use in partial fraction expansion to derive the inverse Z transform. Okay, so for higher order, so you have HRN here, and then you have second order here. So HRN here, and then it's alpha Z minus 1 to the 1 minus alpha Z minus 1 to a square. And I think to even higher power, then it gets ugly, so we don't have a formula here. And but anyway, so for the second power, we have the formula here, and also for the other way around. So so for the RC being the other direction, the smaller than alpha, then we have the say algebraic expression here, and you also take this thing and times the HR minus HRN here. Okay. And yeah, and then we have some sine and cosine, and R to the n. R to the n times sine and cosine here, and this can be done by doing by breaking our sine and cosine to complex exponentials, I believe. Anyway, yeah. Any question? I guess. Anyway, those are also true. But we didn't derive that, I believe. Okay. And anyway, so that's a small review of the nice Z transform pairs. And then we go to this next topic of more analysis of LTI system using a Z transform. And basically what we are doing is we use a convolution property, and we see that the Z transform Y output equal to Z transform of the impulse response times the Z transform of the input. And then we'll say this Z transform of the system function is very nice to analyze our system. And this is Z transform of the impulse function. Just like before, we call this the system function. And it will tell us a lot about the system. Okay. And so in particular, we will think about how causality and the stability of the system. I think it should be causal. It says signal here, but it's weird. It should say it's causal and a stable system. Okay. Although we are thinking about causal is a bit misused. We are thinking about causal and the stable small h. But yeah, but we need to remember causal and stable are system properties of systems, and just that for LTI system we can represent our system with our impulse response. And anyway, so we have causal LTI system, and the LTI system can be expressed by its impulse response small h over n. And if it's causal, then from chapter 2 we know that for causal system h over n equals to 0 where n is less than 0. Okay. And then now we want to see what does this mean for Z transform. Okay, so first thing is h of n equals 0 for n less than 0 means that this is right-sided. So I guess let's try to do some drawing so we'll remember what this is like. So causal means that so this is h of n here, so it's entanglement. Causal means h of n is start from n equals to 0, so it's all 0 when n less than 0. Okay, so it only has things when n is greater than 0. It's something here like this. Okay, and this is right-sided, means that you might extend to infinity to right side, and but more importantly, means that it has a boundary on the left side here. So it only started at some time, and here is n equals 0. Okay, so it's right-sided, and from the property we know in section 10.2, we know that the RC must be the exterior of a circle, so it must be like outside of something and extend to infinity all the way around the circle. So kind of like this. Is outside of a circle extend to infinity. Okay, and then now we compare to chapter 9. Chapter 9 was saying that this being exterior of circle only correspond to right-sided. And in chapter 9 we didn't know that how to enforce that we are actually starting at 0, not starting at say n equal to -1. But here we can actually check that because we can check this infinity thing. So we think about this thing, okay, and so if it is causal, and we think about big H of Z as this power series of expansion of small h of n. So it's small h of n times e to the minus n summation, and usually from minus infinity to plus infinity. But it's causal, so n only from 0 to plus infinity. So we see that this thing has no positive power over Z, and so this thing will converge at Z equal infinity, and so this is actually if only if here. Okay, and so now I guess I'll start with the if. So if this is causal, then the RC will also include infinity. Okay, and so we see that if it's causal, then RC will be a circle outside, so like this picture. Outside of a circle extend to infinity and actually including infinity. And so we're saying this by like if conditions, but if you think about this, actually both of those statements are if only if, and so we get this red box here. So we see that for discrete and LTI system, If you want to check its causal, then you need to check these two things. So the ROC is the exterior of a circle, and it includes infinity. Okay. And yeah, so this is a little different from Laplace transform. Laplace transform, we were saying that if it's causal, then it's like right-sided to something, but we cannot really check whether we were saying that the reverse is not necessarily true, but here we can check that the reverse is true by checking whether or not the ROC including infinity. Okay, and the other thing is we can check what if we are rational. Then rational we have a bit easier checking. So rational, then we also want to check these two conditions. So first one is we want to check is exterior outside outside of the RAM almost pole, and then including infinity. For a rational system, it can be checked pretty easy because the rational system is some polynomial divided by another polynomial. So some polynomial I should write. You have some polynomial numerator of z divided by some denominator of z, and you want this ratio to be finite when z equal to infinity. That means the order here must be less or equal to the order here, or the order of it cannot be greater, so it's less or equal to is here. So order of this thing is less or equal to order of this thing, so that when z equal to infinity, you have a finite number. Okay, so yeah, that's causality. And let's check quickly. So we have some system function like this. Okay. And it has two parts: 1 over 1 minus 1 over 2 z minus 1 plus 1 over 1 minus 2 z minus 1 with z greater than 2. So this thing has a pole at z equal to 1 over 2 and another pole at z equal to 2 here. And then we are taking the almost ROC here. Okay. And so we want to check whether this is rational. Then, as we said, we need to check two things. Okay, so we need to check that it is the ROC is almost ROC extending to infinity, and that checks out because this z greater than 2 is well, as we draw in the picture, is almost extend to z to infinity, and then we need to check that this thing actually converge for z equal to infinity, and yeah, and so we do the rational checking. So this is actually a rational function because if you try to add these two things together with a common denominator and then multiply enough z so that this is a rational function. So we have the numerator divided by denominator 2z squared. Then we see the power of the numerator is 2 here, and the power of the denominator is 2 here. So this is yeah. So power of the numerator greater than power of the denominator. So this thing is finite when z equal to infinity. So when z equal to infinity, this is just 2 here. And yeah, so this should be causal. And I guess another way to check this is when you go to z equal to infinity, then this becomes 0, this becomes 0. And then just 1 plus 1 equals 2, and that's consistent with the checking here. So z equal to infinity is 2z squared over z squared, then it's just 2. Okay, so we think this system is causal because it satisfies both conditions. The ROC is the almost ring, and exterior of a circle, and also z equal to infinity is a finite value. And also we can do direct checking, so it's already in partial fraction, so we can do inversion by the partial fraction expansion. And so this is should be u times a to a to the n, u of n times u u of n with a equal to 1 over 2 and 2. So 1 over 2 to the n plus 2 to the n times u of n. Okay, and yeah, so we see because of this u of n here, then this system is causal. And yeah, this is consistent with what we predict from the property. So ROC is almost in, and including, and also ROC including infinity, then ROC System N is causal. Question? And if not, then C stability. So stability is quite easy. So just like in the Laplace transform case, so the system is stable if only if the RC including the Fourier transform part, which is the unit circle. So observer z equal to 1. Okay. And yeah, the system is stable. Although this definition, this derivation is a bit shaky, but we think the system is stable if only if it has a Fourier transform converge. Okay. So, and that means that the RC including this Fourier transform circle, which is a unit circle, is equal to 1. And here we have the example of a Laplace transform here. So remember, in a Laplace transform case, we were saying that we have a similar argument saying that the system is stable if only if the RC including this Fourier transform line, which is the imaginary axis. Okay, so here we say that the system is stable if only if we include the RC include the unit circle here. Okay, and let's go back to see the same example. Okay. So the same example, h of z equal to 1 over 1 minus 1 over 2 z minus 1 plus 1 over 1 minus 2 z minus 1 with z greater than 2. And we know h of n is 1 over 2 to the n plus 2 to the n u of n. Okay. And okay, and we say the RC was like outside of 2 equal outside of z greater than 2. So this greater than 2, then it doesn't include z equal to 1. So this is unstable. Okay. From the RC analysis of our z domain, then we see that the system is not stable. And we can also see just from here. So this h of n is the 2 to the n part. And so we know that the system is not stable because this is the h of n is not absolutely summable. It has a 2 to n part is exponential growing, and if sum from n to 0 to infinity, it is going to blow up. Okay, and yeah, so let's check out for this signal is our signal include unit circle, and the system is indeed unstable. The system associated with this impulsive response is unstable. And then now we can think about if we have this algebraic expression, and it has a point 1 over 2 and a point 2, and which RC will make it stable. It is so it basically has 3 RC. You can pick the almost RC, which is z greater than 2. Then or you can put the inner ring, so z between 1 over 2 and 2, and then you can choose the innermost circle, z less than 1 over 2. And you want the system to be stable, you want the RC to include the unit circle, so you choose this RC between 1 over 2 and 2. Okay. And then if you RC choose this, we think that the system should be stable, but it's not causal anymore because it's another almost RC. And if you choose the RC between 1 over 2 and 2, then you will see that our small h of z, so this partial fraction expansion invert to, so this one will invert to the outside because its z is greater than the pole here, so invert to one side, so it's still 1 over 2 to the u of n. But this part will invert it to the inside inversion, so it is minus a to the n times u of minus n minus 1. Okay. And so you plot this h of n, then for the positive part, for n being positive, you have this 1 over 2 to the n, so it is exponential decay. And for the negative part, you have this minus 2 to the n. But for 2 to the n for n less than 1 is, 2 to the n for n less than 0 is actually also exponential decay to n to minus infinity. Okay. It's exponential decay to negative n. Okay. And so you see that you have exponential decay on both the right hand side, and the left hand side. I guess positive n and negative n. And this thing is actually absolutely summable and gives you a stable system, correspond to a stable system. And but you also see that this is not causal because you have this n less than 0 part. Okay, and yeah, so that satisfy our prediction. Okay, and then we can think about the latest ROC. The least possible ROC. Okay, so we have to choose. So for this algebraic expression in the system with two possible ROC. So the almost one is causal, and the in between one is stable but not causal because it includes unit circle, but it's not almost one. And then we can think about what if ROC is the innermost one. So ROC is z less than one half, and so it's not causal and not stable because it's not almost almost it's the almost ROC, and it doesn't include the unit circle. Okay, and but anyway, we can still do inversely transform using the partial fraction expansion, and we see that it is minus 1 over 2 to n plus 2 to n and u of minus n minus 2. And so you see that this is not causal because everything, well, because on n less than 0 you have a lot of signal here, and it is not stable because it's 1 over 2 to the n. On the negative n is going to be exponential growing, so this is not absolutely insummable. Okay. And then we have this one sentence here that says something interesting, and that's also had a counterpart in the Laplace transform. That is, if you want the system, a rational system, to be both causal and stable, then all the poles must be inside the unit circle. Okay? Because when you choose the almost ROC must be outside your pole. Then you need to include the unit circle. That means the almost pole must be inside unit circle. So almost pole is inside unit circle. That means all the poles are inside unit circle. And this is similar to the statement in the Laplace transform, where we say if you want to be both rational and stable. Okay. So we want both rational and stable. And so for Laplace transform, we say that we want the system to be both rational and stable. Then all the poles must be left-sided of this purely this imaginary axis. And now it's similar, so it says you want to be not rational and stable. It's causal and stable. Okay, causal and stable. If you want to be causal and stable, then then all the poles must be inside this unit circle. Okay, and let's see more example. Okay, and here is an example of second order system. We didn't derive the second order system, but we just say it's system function will look like this. So system function, just say the solution is 1 over 1 minus 2r cosine theta z to the minus 1 plus r squared z to the minus 2. And you can solve a pole, so it's a pole by solving this second order equation here. And the pole will be r e to the j theta and r e to the minus j theta. Okay. And so they kind of look at this. So it's a radius r and the plus theta and minus theta, and the radius r and plus theta minus theta. Okay, and okay, so if we want it to be causal, then we can think about when will this thing be stable. And assuming causal, then we know the ROC is outside of the almost pole, which are those two poles, so at the radius r. So we see the ROC will be, if it's causal, then ROC will be outside of radius r. And then we want it to be both stable, then we see that we want r to be less than 1. Okay. So only when r less than 1, this ROC of bigger than radius r, we're including this unit circle of radius equal to 1. So here we have another example where r is greater than 1, then we see this ROC outside radius r doesn't include the unit circle, so this is not stable. And then if you actually know this second order equation, then you see that this is makes a lot of sense because you think this r parameter when it's greater than 1 will make your system unstable when you actually see the differential equation. But for now, we just give us an example, seeing that you tune this r parameter here, and you see that when it's greater than 1, you get an unstable system because the poles will be, the causal system will become unstable because the poles are outside of this unit circle here. Okay, and then I think, oh no, we have a lot of things to talk about. I think it will be about correct time. Anyway, so that's causality and stability, and so now we learn a lot, and we will do a lot of analysis of system. And before that, let's do analysis of our linear constant coefficient difference equation by doing this Z transform analysis. Okay, so we have a linear constant coefficient difference equation. So for example, equation like this. And remember the difference equation we have, okay, so we have a linear combination of y and a linear combination of x with some difference. Difference meaning that you do some time shift here. So y of n minus 1, x of n, x of n minus 1, etc. And here we just have a particular example. So y of n minus 1 over 2, y of n minus 1 equal to x of n plus 1 over 3, x of n minus 1. And then we try to solve this difference equation, just like we always do, by applying the transform on both sides. So yeah, and applying the transform on both sides, then we can make this time shift into something nice. So small y become big Y, and linearity is linearity, but this minus 1 here, this time shift, just become extra power of z to the minus 1. So you have a small 0 minus 1 here, and 0 minus 1 here, and this minus 1 becomes z minus 1 here. Okay, and so you see that you can write big Y as big X times something, because this 1 and 1 over 2 z to the minus 1 can factor out. So big Y equal to big X times 1 plus 1 over 3z minus 1 divided by this 1 minus 1 over 2z minus 1. Okay. And yeah, so you can write big Y as big X times some function of z, or a function of z minus 1. Okay, and then if we believe our convolution formula, then we see that big H of z should equal to big Y divided by big X, which is just this thing here. So 1 plus 1 over 3z minus 1 over 1 minus 1 over 2z minus 1. Okay, and okay, so this tells us the system function associated with this linear constant coefficient difference equation. So we have the algebraic form of big H of z here. But we actually don't know the total z transform because this is incomplete. Okay. So this only tells us the algebraic equation, but we don't know the RLC. And in particular, this thing has a pole at z equal to 1 over 2 here. Okay. So there are possible RLC because I guess that's true. Okay, so it has a pole at z equal to 1 over 2. Okay, and yeah, so there are two possible RLC, outside or inside, and that can be determined by many things. And for example, you can have initial race condition, and that will tell you that your system is causal, or you can choose other things. Okay, and anyway, so because the system needs more condition to be totally determined, the relation between x and y, so you can calculate the system function here. So just like Laplace transform, by just a differential or difference equation, you can get the system function. But then you need to, if you want to totally determine, the algebraic part of the system function. But if you want to tell the actual system function, including RLC, you need other conditions to specify it. Okay, and so there are two possible RLC, and so if RLC is greater than is z greater than 1 over 2, as we said, there is a point z equal to 1 over 2, then we can try to do inverse Z transform. Okay, and inverse Z transform, obviously we can do partial fraction expansion, and but here we also do something a little smarter. We write this as 1 plus 1 over 3 z minus 1 times this thing we already know Z transform. Okay, so this thing we already know Z transform is 1 over 2 to the n u of n. Okay, and so we use the linearity and time shift to get the Z transform of this thing. Okay, so you have one part and 1 over 3 times the z minus 1 part. Okay, so the 1 part, you just get this z transform this part, and with the RC being outside, so RC is z greater than 1 over 2. Okay, and so this is our usual a to the n u over n, and with a equal to 1 over 2. And this is 1 over 3 z minus 1, so 1 over 3 just have plus 1 over 3 here. And z minus 1 we can get from doing the time shift. So we get z minus 1 here, so every n got a minus 1. Okay, so z minus 1 here, so n become n minus 1, and u over n become u over n minus 1. Okay. So yeah, so this is also yeah, so this is our response, and we see that this system is causal as or expected because it's almost RC, and also this includes infinity. Okay, so this is causal, and this is also stable because the RC will include in the unit circle. Okay. And if you choose the other RC, and we can also do inversely transform. Okay. And you pick the inside RC, then this 1 over 1 minus a z minus 1 becomes this minus a to the n u over minus n minus 1. Okay. So yeah. So and then similarly, then you have this 1 over 3 give you 1 over 3 here, and you change over n to n minus 1 here. So n to n minus 1 and minus n minus 1 equal to change n to n minus 1 equal to minus n. Okay, and the system will be anti-causal and unstable. Okay, and yeah, so that's an example. And in general, you can have so we have a very general expression here for our linear constant coefficient difference equation. So you have a summation, linear combination summation ak y over n minus k equal to summation bk x over n minus k, and they do z transform on both sides and move things around. Then you see big Y divided by bx is the summation of bk things, summation bk z to the minus k. So z to the minus k here, and then over summation ak z to the minus k, z to the minus k. So you see this original function over z and minus z. Okay. And as we say, here we only have the algebraic part of h of z, and this didn't tell you where the RC. But if you also say the system function, the system is causal stable, then you can pick the RC. Okay. And actually solve your system. And for example, okay, so we try to, okay, yeah, so this is about the linear constant difference equation. Any question? Okay, and if not, then let's see, I think one more. Let's see. We have 2 more problems associated with the properties of the transform. Okay, and yeah. So let's suppose we are given this information about your TI system. So we are given input-output pair. So so let's say when our input is this kind of exponential function x1 of n equal to 1 over 6 to the n u of n, and we know that when input is this, then output is some real a times 1 over 2 to the n plus 10 times 1 over 3 to the n u of n. And so we know this input-output pair, and we know another input-output pair. We know x2 of n equal to minus 1 to the n, then y2 of n equal to 7 over 4 minus 1 to n. Okay. And we show that with these 2 information we can learn a lot of things. So we can learn not this or this. With these 2 things we can learn the system function x of z, and we can learn the value of a, and we can learn other properties like stability or causality. Okay, and let's see how this works. So how this works is first we do Z transform on both of these. Okay, so we see that x1, so we have this small x1 transform to go through C3 to big y1, and then we do Z transform on both of them, and x1 will, okay, let's just start here. So x1 will transform to this, well, it's our favorite with a equal to 1 over 6. It's 1 over 1 minus a z minus 1, and it's a right-sided one, so its RC is outside of this pole at 1 over 6. And then y1 is similar, so you have so small y1 is similar. It's a linear combination of those two things, and so this part will transform to a over 1 minus 1 over 2 from this 1 over 2 z minus 1, and this part is 10 over 1 minus 1 over 3 from this 1 over 3 z minus 1. Okay, and so this is the pole at 1 over 2, this is pole at 1 over 3, and the pole should be, so it's a right-sided function, so both of these should pick the outside. So the RC should be intersection of outside 1 over 2 and outside 1 over 3. So RC should be outside of everything. So RC should be outside 1 over 2. Okay, and yeah, and you try to combine those two terms, then it's this complicated expression. Okay, and but we know y1 equal to h times x1, and big Y should equal to big H times big X, and so big H should equal to this big Y divided by big X, and so big Y divided by big X, and the algebraic expression is this thing. And yeah, so it's very complicated, but it has this thing, and divided by big X, and so you have 1 over this thing, and dividing, so it's just this thing, 1 minus 1 over 6, z minus 1. Okay, and so we get a C-sum function, the algebraic expression of a C-sum function, and here with a still undetermined. Okay, and then that's the first how we use the first condition. And the second condition, we do this. We have seen this twice, and second condition we use it a bit differently. We didn't do the transform. We think about it being the we think about big H being the eigenvalue of eigenfunctions, because we know z to the minus z to the n is the z to the n is the eigenvalue. So so I guess let's write this again because we always forgot. So we know that z to the n is the eigenfunction of every LTI system, with eigenvalue being h of z, and so it becomes h of z to the n. Okay, and okay, so we know z to the n is for every z is eigenfunction of every LTI system, and with eigenvalue being h of z, and yeah. And so we see that x2 has actually has this form z to the n, so with z equal to minus 1. So we know minus 1 to the n should be should transform to h of minus 1 times minus 1 to the n. And that indeed check out. So h2 of n is also something times minus 1 to the n. So minus 1 to the n here. And yeah, and so you know this minus 1 to the n times h of minus 1. So here you know h of minus 1 will equal to this h number 7 over 4 here. So h of minus 1 equal to 7 over 4, but we also have an expression of x, h with some unknown z here. Okay, and so you put z equal to minus 1 to this expression, then you see that you get the expression of a here. So you have 7 over 4 equal to this expression of a, and this is actually a linear equation of a, and you can solve it, and you will find a equal to minus 9. Okay, so as we clean, then we find the big H and a from just those two conditions. So h of z will equal to, so you now plug in h of a equal to minus 9 back, and you get h of z equal to this 1 minus 2 z minus 1 times 1 minus 1 over 6 z to the minus 1 over 1 minus 1 over 2 z minus 1 times 1 minus 1 over 3 z minus 1. Okay, so this is our h of z, or you can try to make it into a rational function of z, and it will look like this. Okay, and then finally, I guess the hardest part of this question is, so now we know the algebraic part, then we also want to know the we also want to know the RC of this thing. So where is the RC of this thing? And okay, and so this thing you can also actually also know the RC of this thing by thinking about the RC of x and y. Okay, so let's first draw this thing. So from this expression we see that there are two poles. There is a pole at 1 over 2 and a pole at 1 over 3. Pole at 1 over 2 and a pole at 1 over 3. And so there are three possible RC. You can be outside of 1 over 2, or you can be between 1 over 2 and 1 over 3, or you can be inside 1 over 3. But then you look at this expression, and then you remember that the RC of y must include the intersection of RC of h and the RC of x. Okay, this is what we have in the convolution formula, and we have a similar argument in Laplace transform. So RC of y1 must include the intersection of RC of h and the RC of x1. And we know RC of y1 and RC of x1. It was before, it was here and here. So RC of x1 is greater than 1 over 6, and the RC of y1 is greater than 1 over 2. And now, okay, so now the detailed derivation is a bit more complicated. And so basically, you see the RC is x1 is greater than 1 over 6, then it's basically by process of elimination. So you see RC of x is greater than 1 over 6, and so if your RC of h is less than 1 over 3, then the intersection between RC of h and RC of x, okay. So I guess this name is too long. So let's say this you have this is R sub big Y, and you have R sub h. Okay, let's give it some names. So for Y you have R sub Y, and you have R sub h here, and R sub x here. R sub x here, and you know. No, it's too complicated. So you have those three R sub y, R sub h, and R sub x. Okay, and so now you think about the intersection between R sub h and R sub x. And so if R sub h is less than 1 over 3, then you see that in the intersection with R sub x. Okay, so maybe let's draw this a bit better like this. So this thing is R sub x, and this thing is R sub y, and then we have R sub h question mark. And then what we do is we look at the intersection between R sub x and R sub h. And so if R sub h is less than 1 over 3, then it has an intersection between these 1 over 6 and 1 over 3. But that's not inside R sub y, so that's impossible, because R sub y must include in every intersection between R sub x and R sub h. So we are checking the intersection of R sub x and R sub h. And similarly, if your R sub h is between 1 over 3 and 1 over 2, then its intersection with R sub x is still has this 1 over 3 and 1 over 2, and that's not inside R sub y, and that's not possible. And so those two are not possible, and the only possible is the last one. And just to be careful, let's check that the last one gives the correct is also the last one is also good. So if R sub h is outside of 1 over 2, then its intersection with R sub x is indeed outside 1 over 2, and its inside is R sub y. Okay, so everyone okay with this a bit complicated derivation? So we check whether R sub x and intersection with R sub y, R sub x intersection with R sub h is inside Ry. And then we see that the only possibility is R sub h is outside 1/2. Okay, and yeah, so now we know the ROC is outside 1/2, and then we can know the, or more generally, we know the ROC. We know the ROC and the algebraic part. Then we can check the stability and the causality of the system. Okay, and so stability is easy. So just check does the ROC equal the z equal to 1. The radius equal to 1 circle, and indeed including the unit circle, and we know the system is stable. Okay. And then to see that whether the system is causal, we need to check two things. So first is the ROC is almost the outside of almost circle here, outside outside of a circle here, and that's good, means your small h is right-sided, and also we need to see whether this h of z include infinity, where when z goes to infinity, these converge, and yeah, you can take z goes to infinity and see that this converge is when z goes to infinity is just 1. So the system is also causal. Okay. And yeah. And yeah, so we know that the system is stable and causal. And from this equation, from this system function here, we can also write the corresponding difference equation. So just we just know those correspond to x and those correspond to y. So this 1 give you x over, and this minus 13/6 give you minus 13/6, and z minus 1 give you a minus 1, and 1/3, 1/3, minus 2, minus 2. And similarly, those are the are the coefficients of y. So 1 give you 1/1, and then minus minus 5/6 here, and then minus 1, and minus 1, 1/6, 1/6, and then minus 2, minus 2. And then if you want the system, okay, so this is only algebraic part, and but we also know our system is causal. So if you want our differential equation to pick the ROC as we solve here, then we can say the system is stable, or we can have a condition of initial rest, which will also give you we can say the system is stable, or we can say we have a condition of initial rest, meaning that the system is causal, and that will also give you the almost ROC. Okay, and we have 2 more minutes, and let's try to finish a little bit of the next question. Okay, and so here is a kind of a true and false question, but okay, but we don't have time to give you a try. But we have some condition here, and we will try to determine whether more conditions are true or false, or doesn't know. Okay. And so we have that we have some impulse response, and the system is stable and causal, and we have some condition or big H of z. So we know H of z I guess that H of z contain the pole at z equal to 1/2. Oh, sorry. So H of z contain a pole at z equal to 1/2, and 0 somewhere on unit circle. Yeah. So pole at z equal to 1/2, and 0 somewhere on unit circle. 0 somewhere. And there are other points at 0. And then we have those 5 things to check. And so first one is whether f of 1/2 to the n, h of n converge. And this can be checked by knowing that this is a Fourier transform at r equal to 2. Yeah. But I guess yeah. Sorry, we are over time, and so I guess you can read the slide for this last question, and this will be the yeah, this will be the length of the course, and yeah. So we have a lot of tests on the final on next Friday, including both Fourier transform on chapter 4 and chapter 5, and also Laplace transform on Laplace transform on chapter 9 and Z transform on chapter 10. And I guess the scope of chapter 10 is until here, but we have some interesting leftover. So we have the block diagram and unilateral Z transform. That's kind of similar to Laplace transform, but it's the end of the slide. So if you are really interested, you can check that. That's not in the final. But in the final, we see that we see that we have a lot of ways to analyze our TI system. We have both of the Fourier transform, and this is Laplace transform and Z transform, and yeah. So hopefully you have fun in this class, and yeah, we'll take the final on next Friday. Yeah. So thank you.